Okay, so first things first, before we even really get into physics per se, we have to talk about a few just kind of general science things. And in particular, I want to talk about what separates science from math. So in math class, it's perfectly fine to put down the number 5. There's nothing wrong with that. But out in the real world, which is, science is basically talking about the real world, 5 is not a useful piece of information. For instance, if someone says, how far down the street do I have to go to get to the library, and you say 5, that's not helpful at all to them, because it's 5 of what? So is it 5 blocks? Is it 5 stoplights? Is it 5 miles, 5 kilometers? 5 of what? So in physics, along with every number, we have what's called a unit. So again, 5 miles. So that'd be the number is 5 and the unit is miles. So it tells you how many of what. So in this class, all quantities need units. You should never have a number just hanging out by itself. You should always have some kind of associated unit. There is one exception, ratios of like quantities. So like quantities. So an example would be, if you've traveled 5 miles and you want to walk a total of 10 miles, the ratio there, canceling the miles, is a half. So if you've walked 5 miles of your intended 10 miles, you've walked halfway. And notice the units have canceled, so you basically have a quantity which does not have any units. And that's important because if you walked halfway, it's halfway no matter how you might choose to measure the distance. If you measured it in miles or kilometers, whatever you decided to use, whatever way you want to quantify distance, if you walked half of it, you're halfway there. So we'll come up with certain things that we will note are these special kind of ratios of like quantities, but everything else needs units. And so what we need to do is talk about the unit system that we'll be using in this class. It's called the SI units. The SI stands for System International, which, even if your French is rusty, you probably know that means international system. So this is the scientific community's internationally agreed upon set of units. And so for all the different types of quantities that you might want to talk about, there's a kind of a standard bearer. So for instance, in this class, we'll want to talk about length. We'll want to talk about time, mass, and angle. Now there are others, but these are the 4 that we will need for this class. The standard bearer for length in the SI units is a meter, abbreviated M. Okay, M does not stand for miles. Generally, if we want to abbreviate miles, we use MI. So I might have written this as MI. But what we generally want to do is talk about lengths in terms of meters. Okay. Now, if there were certain parts of the world, like Europe or something like that, that happens to also be the everyday language of length. So you walk up to an average person on the street and they can tell you exactly how many meters tall they are. It's because the layman's offshoot of the SI units is called the metric system. So if you're not used to dealing in meters, then let me give you some idea of how much a meter is. A meter is 3.3 feet, or if you want, just over a yard. And just to give you some intuition about how much a meter is, and this kind of intuition is important, probably everyone you know is somewhere between 1.5 meters and 2 meters tall. So this is kind of the, most people are in this range, okay? So just to give you an idea, if you're 1.5 meters tall, you're about 4'11", okay? So that's on the shorter side. And if you're 2 meters tall, that brings you right up to about 6'7". Okay, so you can see most people are in this range. You'll probably get the biggest intuition about what a meter is once you get in the lab and you start handling the meter sticks. The meter sticks are, about 3 feet long. And we do also have 2 meter sticks, which are quite long, so be careful when you swing them around. They are not something that is easy to kind of maneuver. They will certainly poke out from the edge of your lab table. So that's a meter. There are certainly other units for length, but that's the one we'll generally use. And for time, we use a second. So this is something that everyone has an intuition about how much a second is, even though they might use meters in Europe and feet here and miles and things like that. Everyone uses the same kind of time, so everyone kind of knows what a second is. So we can kind of move on from there. For mass, we use something called a kilogram, or kg, abbreviated for short. And again, if you walk up to the average person on the street in Europe, they know exactly how many kilos they are. Kilos is short for kilogram. If you want to get some kind of idea of how much a kilogram is intuitively, a kilogram is about just over 2 pounds, okay? Now I put an asterisk there because it turns out that's not always true. That's only true near the surface of Earth. Of course, that's where we'll stay for the time being. We won't go up into space for another couple weeks. But it turns out that I need to put this, kind of plant this in your mind, because we will come back to this around homework number 6 and figure out what's going on here. Now, 1 meter is always 3.3 feet. That's just a definitional thing, how they've been defined. They're both lengths. It turns out that 1 kilogram is a mass, but 2.2 pounds is not. So there's these two, their correspondence changes depending on where you are, whereas 1.1 meter is 1 meter is 3.3 feet anywhere in the universe. We move forward then to angle. And so for angle, we're going to use, for SI, radians, or rad. And this may not be familiar in terms of if you don't know the term, but you may have used the radians mode on your calculator. What radian mode is when you want to work in angles in terms of pi, okay? So just to give you an idea, 2 pi radians, 1 full circle, is also 360 degrees. Or you can call it 1 revolution if you want. Those are 3 different ways to talk about angle, in terms of pi, in terms of degrees, in terms of revolutions. There are others, but only radians is in the SI, okay? To give you another way to visualize a radian, if you imagine you have a slice of pizza, so a slice of pizza like this, okay, and let's say that the distance from the middle of the pizza out to the crust, let's call that L, and of course that's the same distance L here. That's going to be true of any pizza slice, no matter how big or small. These are the distances from the point to the crust, as long as you are cutting from the middle of the pizza, of course. But let's suppose that your slice of pizza, the distance along the crust is exactly the same as these distances, okay? So that obviously depends on the slice of how big of a piece of pizza you're going to take. Well, this amount of angle is 1 radian, okay? That amount of angle is roughly about 57 degrees. And so if you want to take slices this big and you want to make a full pie, so a full pizza, I should say. Pie is a loaded word here, so if you want to make a full pizza, it turns out that it takes about 6.28 of these slices, 6.28 radians, to make 360 degrees. And 6.28, well, that's just 2 times pi, okay? Obviously, pi is not exactly, but that's close enough. So, radians is when we really get serious about angle, we're going to have to work in radians. That won't probably happen until maybe homework 8 or so. So, oftentimes we'll kind of cheat and use degrees a lot at the beginning of the course. But remember in the back of your mind that when we really have to go fully into SI units, we've got to use radians. Okay? So, these are our standard bearers, and because they're so important, they're the building blocks of the SI units. All of these things are very well defined. Now you might say, well, isn't it easy to define a meter? Well, if you're trying to define it exactly, precisely, you actually have to go to a lot of trouble to make sure that everyone knows what you mean by a meter in a very, very, very high degree of precision. Same with, what does 1 second mean exactly? You might say, isn't that just a fraction of a day? Well, it turns out that a day varies in length, so you have some problems there. There are some esoteric ways of doing this by defining these. Just in brief, a meter involves how fast a light travels in a certain time. A second is defined by this vibration of a crystal, which is incredibly regular. The one that I will mention, the kilogram, basically the standard bearer for a kilogram is a metal cylinder in a glass case in France. And I'm not saying that that particular object is the closest thing to a kilogram. It is a kilogram by definition. That object has been decided to be the amount of mass which is equivalent to a kilogram. And if you want to know to a very high degree of precision if your block from somewhere else is 1 kilogram, the best thing you can do is put it in a briefcase, fly it to France, and compare it and see if it's more or less than this one. And in fact, that's exactly what's been done. There's a set of copies that have been carefully compared to the standard bearing kilogram and then shipped out to different parts of the world, so people don't have to necessarily get on a plane to do this. So these are all very well and carefully defined because scientists need to be able to talk about a huge number of meters or a tiniest fraction of a meter or a huge number of seconds or whatever, and they need to make sure that there's no compounding error in this. So let's label these guys. These are going to be our fundamental units. Fundamental units. Okay, these are our building blocks. Everything we do is kind of built off of these. Now, later on, we're going to have these things called composite units. And composite units, they're not different, they're not completely independent things like this. They are combinations of these more fundamental units. I can already give you a couple that you might recognize. So for instance, if we wanted to measure a speed is measured in meters per second. So length per time. So there's no new units there. It's made from a meter and a second, 2 of the fundamental units. Here's another one. Let's say you wanted to talk about an area, right? That's a square meter, okay? So how many square meters is some area? It's not a new unit. It is a combination, or in this case, just using it squared, one of these units. So we'll be coming up with all sorts of composite units through the semester. We'll be talking about force and energy and momentum, and those things all have composite units, which are some combinations of these. Okay. Now, to assist you, I've posted a units guide on the course webpage and WebAssign. So this is something I'd recommend that you print out sooner rather than later, and it's a handy reference as we go through the semester. You can kind of see, as we introduce new composite units, what are they combinations of, what are typical variables that are used for them, things like that. So, and if you ever were wondering what the units of something are, you can refer to it. I should mention that this units guide also is called the units and prefix guide, because it also talks about something called prefixes. So that's the next thing I want to talk about. What is a prefix? So this is a kind of an abbreviation. So let's say I have the number 3.2 times 10 to the minus 9 seconds. Okay, so that's a very short time. Now this is a lot to write. If you were trying to type this, it'd be annoying because you have this exponent and things like that. So what we might do is we look up a prefix. Now again, you'll find a complete list of prefixes in the guide I was just talking about. You will also find the most common ones we actually need on exams. You'll find those on the exam formula sheet as well. So I would also recommend that you download and print that as soon as possible. Okay, so again, you'll find them in the units and prefix guide, and you'll find the most common ones on the exam formula sheets, exam equation sheet. Okay, so I definitely recommend printing out those. So those are the things that you will get given at exam, so it's really good to know ahead of time what's on them, what's not. So if you go to one of these two resources, you'll notice that a way to abbreviate 10 to the minus 9 is by the letter N, which is nano. Okay, so you can also write this as 3.2 nanoseconds. Okay, so you can see that's very convenient, but I do want to caution you that what you're doing there in essence is, let me write this out so it's more side by side. What you're doing is shuffling what is where. So here, the number is 3.2 times 10 to the minus 9. The unit is seconds. But over here, now it's 3.2, that's the number, and nanoseconds is the unit. So what you've in essence done is taking a part of what used to be the number, and you've instead transferred it into the unit. So that's not insignificant. And so what you need to be aware of is that if you have a prefix on there, then it's no longer SI. So this quantity is SI, and this, even though it's the exact same amount, it's non-SI. Okay? And the reason why is much in the same way that you could look up 1 meter is 3.3 feet. Okay, this is SI, but this is not. Anytime you start messing with the units, even if it's just with a prefix, then you are moving it out of the baseline fundamental units that we want to use. Okay, so for instance, if you were had a problem and you were trying to figure out what to plug in for the number, you should plug in 3.2 times 10 to the minus 9. Not just 3.2, but 3.2 times 10 to the minus 9. So SI units, let's make a little box here. We said meters, seconds, radians, and kilograms. They have to be exactly those. Either no prefix at all with meters, seconds, and radians, and for kilograms, that actually has a prefix already. Kilograms, kilo is 10 to the 3. Okay? So this is the kind of the odd one out. Kilograms is SI, but grams is not. So this one has to have the right prefix. So not SI units, I'll put that as anything outside the box. Just like nanoseconds is not, that's outside the box, or nanometers. Grams is outside the box, so is nanograms. Okay? So it has to have exactly the right prefix or lack thereof for these three in order to be correct. Other things, obviously, we can do other, we can do kilometers, you can do a kilosecond if you want. There's lots of prefixes. In fact, there's a name usually for every power of 3. You could have micro, that's 10 to the minus 6. You could have a microsecond, or a micrometer, or a microgram. You can have non-SI units that are just feet, or miles, or anything like that, furlongs. There's a whole wide world of units out there, but this is kind of our oasis of calm, okay? So we want to make sure that we have everything, all our lengths are in meters, all our times are in seconds, our angles generally in radians, although again we'll sometimes be able to have it in degrees if we don't plan to do anything with it, and then masses should be in kilograms. And if you see, and this is one of the first orders of business you should look at in your problem, if you see anything that is not in those units, you need to get them into those units, okay? So the reason why is because the SI unit system is what I'll call self-bookkeeping. It kind of takes care of things so you don't have to worry about it. Now I can't really show you how this works because I don't really have any equations yet to show you, but I can't emphasize this enough. You'll kind of appreciate the beauty of this later. And so you want to take advantage of this self-bookkeeping feature so that it will take care of the units so you don't have to stress out about them. Okay, so your first instinct should be to get everything into SI units if it's not already. So I'll talk about that in the next video. What if you do not have something in SI units? What is the process by which you get into this system?